9 minutes. That is how long active region 4513 waited this morning before it fired again. The first flare ended at 10:09 Universal Time. At that exact minute, the next one began. That makes 6 M-class flares out of a single sunspot group in roughly 39 hours, from a region that officially, on paper, is classified as one of the simplest and least dangerous kinds the Sun produces. Every one of those eruptions went somewhere harmless because of where that region happens to be standing. In 2 days, it stops standing there, and nobody can tell you what is actually inside it until it is already too close for the answer to change anything. If you would rather understand this than just hear about it, subscribe to the Skylab because this region is not finished. Drop a comment telling me where you're watching from and whether you have ever seen an aurora with your own eyes. Now, let's get into it. Part 1. The 6 Flares. At 9:57 Universal Time this morning, the Sun fired again. It was not a large flare, an M1.6, which on the scale we use to measure these things, is the kind of event that happens often enough during an active stretch that most people who track the Sun professionally would log it and move on. What made it worth stopping for was what happened 9 minutes later. At 10:09, the first flare ended. At that exact minute, a second one began. It peaked at 10:18, and it was also an M1.6. The region that produced both of them is called active region 4513, and it has now been erupting for the better part of 2 days. Here is the part that should get your attention. Yesterday, the forecasters at the Space Weather Prediction Center in Boulder issued their outlook for the 20th through the 22nd of August. Their assessment was that solar activity would be at low levels, with a chance for isolated M-class flares. That forecast was not wrong. Isolated M-class flares were explicitly allowed for. But there is a difference between a region that sits at the bottom of its forecast envelope and one that keeps pressing against the top of it, and this region has now produced M-class flares on 3 consecutive days. Let me walk you through the whole sequence, because the shape of it matters more than any single event inside it. It started on the 19th of August at 4:54 in the morning Universal Time with a C5 flare. At that point, the region did not even have a number. It was a patch of activity rotating around the eastern edge of the Sun, unremarkable enough that it had not yet been catalogued. A C-class flare is a minor event. On any given day during an active period, the Sun might produce a dozen of them, and nobody would take much notice. Then, at 18:24 that evening, something began. It built for 27 minutes and peaked at 18:51 as an M1.0, and it faded out by 19:10. That was the first M-class flare of the sequence. It was the moment this stopped being an ordinary patch of solar surface and became something worth watching. The next morning, the 20th, at 7:31 Universal Time, the region went again. That one peaked at 8:05 as an M1.8 and produced an R1 radio blackout on the sunlit side of Earth. Minor, barely noticeable, unless you happen to be depending on high-frequency radio at that moment over the affected longitudes. 3.5 hours later, at 11:32, the X-ray sensors on the Goose 18 satellite registered another rise. It came up through C6.1. Then it kept going. At 11:42 Universal Time on the 20th of August 2026, it peaked as an M8.1, and it was still an M4.1 when it finally ended at 11:54. 22 minutes, start to finish. That was the largest solar flare in months. I want to be precise about how large, because the numbering on this scale misleads almost everyone the first time they encounter it. The M8.1 peaked at a measured X-ray flux of 8.12 times 10 to the minus 5 watts per square meter. The threshold for an X-class flare, the top of the scale, is 1 times 10 to the minus 4, which means that flare fell roughly 19% short of X-class. The reason that matters is that the scale is logarithmic. Each letter represents a factor of 10. A C1 is 10 times a B1, an M1 is 10 times a C1, an X1 is 10 times an M1. So when you see M8.1 and X1 written next to each other, your instinct is to read a gap that isn't there. 8.1 is not 81% of the way from M to X. It is much closer than that. It is the same trick your brain plays on you with earthquake magnitudes, where a 7 does not sound twice as bad as a 3.5, and is in fact something like 180,000 times the energy release. The Sun came within a rounding error of an X-class flare, and it did it from a region that had existed as a numbered entity for about a day. 4.5 hours after that, at 1611 Universal Time, it fired again, an M2.9. It is worth pausing on what the rest of the Sun was doing while this was going on, because it puts the behaviour of this one region into perspective. In that same 24-hour period, a brand new region was numbered on the other side of the disk, active region 4514 at South 10 West 49. 2 other regions finished their transit and rotated off the western edge entirely, disappearing around the back of the Sun. That left 4 numbered regions on the visible face of the star, 3 more, catalogued on previous rotations as active regions 4498, 4502 and 4500, were listed as due to return from the far side between the 20th and the 22nd. That is what the Sun normally looks like, a slow turnover. Regions arriving, regions leaving, most of them doing very little on their way past. Out of that entire census, 12 of the 22 flares recorded across the disk in that window came from one region, and it was the newest one on the board. That is 4 M-class flares inside 24 hours from a single region, which is where yesterday's story ended. If you watched our video on that flare, you know the conclusion we landed on. It missed us, and the reason it missed us had nothing to do with luck or mercy. But the region did not stop when the video went up. Overnight it kept working, a C4.1 peaking at 2:01 Universal Time this morning, a C6.7 at 2:20, a C6.2 at 6:35, and then the 2 M1.6s I opened with, at 9:57 and 10:18, 6 M-class flares in approximately 39.5 hours, measured from the peak of the M1.0 on the 19th to the peak of the second M1.6 this morning. 6. There is one more detail in that ledger, and it is the one I would flag above all the others, because it is not about magnitude at all. It is about shape. The 8.1 was what solar physicists call an impulsive flare. It rose fast, peaked hard, and was gone in 22 minutes. A spike. The M1.6 that peaked at 9:57 this morning was a completely different animal. It began at 9:09. It took 48 minutes to reach its peak. It did not finish until 10:09. That is a full hour from onset to end, for a flare roughly 1/5 the strength of the one 2 days ago. That form has a name. It is called a long-duration event, and it matters because of what tends to come with it. Impulsive flares are energy released quickly and locally, and they often stay put. Long-duration events are the flare morphology most reliably associated with coronal mass ejections, which is to say, with the Sun actually throwing material off itself rather than just flashing. When a region's eruptive style shifts from impulsive toward long duration, that is not a change in how loud it is being. It is a change in what it is capable of sending. And then, 9 minutes after that hour-long event finished, it fired again. Think about what that implies. A magnetic field that erupts and then goes quiet for a day is a field that has released its stress and needs time to rebuild. A field that erupts, finishes, and immediately erupts again has not released anything. It is reloading. Whatever is feeding energy into that region is feeding it faster than the region can discharge it. The mechanism behind that is worth understanding, because it is the single thing that determines whether this region matters at all. A solar flare is not combustion. Nothing burns. What happens is that magnetic field lines, twisted and sheared and forced into configurations they do not want to be in, snap into a lower energy arrangement, and the difference between the old configuration and the new one gets dumped into the surrounding plasma in a matter of minutes. Physicists call the stored portion the free magnetic energy, meaning the energy above and beyond what the field would hold if it were simply relaxed. You build free energy in 2 ways. You can twist an existing field by having the plasma at the foot points of the loops shear past itself and wind the loops up like a rope. Or you can push new magnetic flux up through the surface from below, so that fresh field emerges into a space already occupied by an older field pointing a different direction. That second process is called flux emergence, and it is the one that produces regions like this. It is also the one that does not stop just because a flare went off. If new flux is still rising into active region 4513 from the convection zone underneath, then every eruption is relieving stress that is being replaced from below faster than it is being spent, which is exactly what a 9-minute gap between an hour-long event and the next one looks like from the outside. So we have a sunspot group that has been escalating for 2 days, that has just changed the shape of how it erupts, and that appears to be recharging faster than it fires. None of it has come anywhere near Earth. Not one of those 6 flares produced an Earth-directed coronal mass ejection. The Space Weather Prediction Center was explicit about it in their discussion. No Earth-directed CMEs were observed in available coronagraph imagery. The large cloud of plasma that came off the Sun with the M8.1 was tracked heading east, away from the planet, into empty space where it will expand and dissipate and never be seen again by anything that cares. That is not because the Sun aimed away from us. The Sun does not aim. It is because of where the region happens to be standing, and that is going to change. Part 2. The number that should not be there. There is an official document that describes exactly how dangerous active region 4513 is, and it is almost certainly wrong. It is called the Solar Region Summary, and it is compiled jointly by the United States Air Force and NOAA every single day. The one I am working from is number 232, issued at 0030 Universal Time on the 20th of August, with positions valid as of midnight on the 19th. It lists every sunspot region on the visible face of the Sun, where it sits, how large it is, how many spots it contains, and, in the final column, its magnetic classification. For active region 4513, that final column reads Beta. Beta is the simplest classification there is that still counts as a sunspot group at all. It describes a bipolar region, 2 areas of opposite magnetic polarity, one positive, one negative, sitting side by side, cleanly separated with a clear dividing line between them. It is the solar equivalent of a bar magnet lying on a table, tidy, predictable, not the sort of thing that keeps anybody awake. The classification scheme this comes from is called the Mount Wilson system, and it works by escalation. Beta is 2 separated polarities. Beta-gamma is what you get when those polarities start to intermingle along the dividing line, when the boundary stops being a clean line and starts becoming a ragged, interpenetrating mess. And then there is delta. A delta configuration is when opposite magnetic polarities are crammed inside a single sunspot penumbra, within about 2 degrees of each other, with no separation at all. Field lines of opposite direction forced into direct contact and held there by the sheer weight and pressure of the plasma around them. That is a magnetic system under enormous stress, storing energy the way a bent steel beam stores energy, and it is the configuration behind essentially every truly large flare the Sun has ever produced. Beta regions do not do that. Beta regions are not supposed to produce M8 class flares, and a beta region is very much not supposed to produce 6 M-class flares in 40 hours. It is worth knowing where these letters came from, because the scheme is older than most people assume, and it exists for a specific reason. George Ellery Hale established in 1908 that sunspots are magnetic, which was the first time anybody had detected a magnetic field anywhere beyond the Earth. He did it using an effect discovered by Peter Zeeman a decade earlier. When an atom sits inside a magnetic field, the spectral lines it emits split into multiple components, and the width of that split scales with the strength of the field. Point a spectrograph at a sunspot, measure how far the lines have split, and you have measured the magnetic field of another star. That technique is what a magnetogram still is today, industrialized. An instrument scans across the solar disk, measures the Zeeman splitting and the polarization of light at every point, and converts the result into a map of magnetic field strength and direction across the surface. By 1919, Hale and his colleagues at Mount Wilson had enough of those maps to see that sunspot groups fell into recognizable classes of magnetic arrangement, and the classification scheme that came out of that work is, with modifications, the one still in use on the summary I am reading from this morning, which is to say, the letter in that column is not a label somebody assigned by eye. It is the output of a measurement, and measurements have failure modes. It gets stranger when you look at the size. That same summary lists active region 4513 at 100 millionths of the solar hemisphere in area, with 2 sunspots spanning 6 degrees of longitude. Small. Now compare that to the region sitting on the opposite edge of the same Sun on the same day. Active region 4507 at north 4 west 69, 300 millionths of the hemisphere, 13 sunspots, 11 degrees of longitudinal extent. and its magnetic classification is beta gamma delta, which is to say it is the full escalation, the real thing, the only genuinely complex magnetic region anywhere on the visible disk. 3 times the area, more than 6 times the sunspots, the one configuration that is actually known to produce the biggest events, and it produced C-class flares. The small, simple, unremarkable region produced the M8.1. The large, complex, textbook dangerous region produced nothing much at all. If you were handed those 2 entries with no other information and asked which one to watch, you would pick the wrong one, and you would be right to pick the wrong one because on paper, it is the right answer. So what is going on? The answer is geometry, and it is the same geometry that saved us from the flare in the first place. Active region 4513 was sitting at east 81 degrees. That is 81 degrees around the curve of the sun from the centre of the disk as we see it, which puts it within 9 degrees of the edge. You're not looking at that region. You're looking across it, almost exactly edge-on, at a surface that is curving away from you. Everything about that view is compressed. Area foreshortens, so a region that covers a given patch of solar surface appears to cover far less of the disk. That 100 millionths figure is a flaw, not a measurement. The true area is larger, and nobody can currently say by how much. You can put a number on roughly how much, and it is worse than most people would guess. The projection factor for a patch of surface tilted away from you is the cosine of the angle you are viewing it at. At the centre of the disk you are looking straight down, and the factor is 1. At 45 degrees it is about 0.7, so you are seeing 70% of the true area. At 81 degrees east, where this region was, the cosine is roughly 0.16, which means the region's apparent area is something like 1/6 of its actual area. That 100 millionths could correspond to something considerably larger lying flat on the surface. And the correction only ever runs one way. There is no viewing angle that makes a region look bigger than it is, but the real problem is not area, it is polarity. To classify a region's magnetic complexity, you have to measure the magnetic field along the line of sight, and then work out how the positive and negative regions are arranged relative to each other on the solar surface. Face-on, that is a solvable problem. Edge-on, it is not. The separation between 2 polarities collapses towards 0 as you rotate them away from you. Structure that would be plainly visible from the front flattens into an ambiguous smear, and the systematic effect of that flattening is not random. It biases towards simplicity. Complexity requires resolving fine structure, and fine structure is exactly what you lose first, which means the beta classification on active region 4513 is not, in any meaningful sense, a measurement of active region 4513. It is a measurement of our viewing angle, and of all the answers that viewing angle is capable of returning, beta is the least alarming one. There is a date attached to when this stops being a problem. To get a trustworthy magnetogram, a genuine reading of the polarity structure, you need the region somewhere between about 45 and 30 degrees east. Given where it is and how fast it is moving, that puts the first honest classification around the 22nd to 23rd of August. Now hold that date, because we are going to come back to it, and it is going to matter more than almost anything else in this video. There are only 2 ways to resolve the contradiction between what the classification says and what the region has been doing. The first is that the classification is wrong because of the angle. An active region 4513 is substantially more magnetically complex than beta. The second is that the classification is right, and a genuinely simple bipolar region has produced 6 M-class flares in 40 hours, which would put it well outside what its own structure should permit. The first explanation is far more likely. Almost every solar physicist you asked would tell you the same thing without hesitating. Limb classifications are known to be unreliable, and this is exactly the failure mode. This is not a secret, and it is not a criticism of the people producing the summary. The forecasters know. It is why regional descriptions coming off the eastern limb routinely carry hedging language about foreshortened views and provisional classifications, and why nobody in the field treats a limb classification as settled. The number goes in the column because a number has to go in the column. Every day the summary has to say something about every region, including the ones that cannot be properly seen. The alternative is a blank space, and a blank space is not more useful than a provisional answer. But the effect of that convention is that a region arrives on the eastern edge wearing the most reassuring label the geometry can generate, and it keeps wearing that label for days, right up until the moment it rotates far enough to be measured honestly. Anyone reading the summary without knowing this would come away thinking the Sun currently has one complex region and several simple ones. What the Sun actually has is one complex region, several simple ones, and one region nobody can classify at all. It is also the worse answer, because if the region is more complex than beta, then the number in that column is not describing a quiet region. It is describing a region we cannot see properly, and the correction, whenever it comes, only runs in one direction. There is no version of this where the honest measurement comes back and says it is simpler than we thought. Beta is already the flaw, so we are not at this point waiting to find out what this region is going to do. We are waiting to find out what it is, and there is a clock on that question, but the clock was not set by us, and it cannot be stopped, sped up, or negotiated with. It is set by the fact that the Sun turns. Part 3, 13.2 degrees a day. The Sun is not a solid object, and this one fact is about to determine everything. It is a ball of plasma, and different latitudes rotate at different speeds. The equator goes around fastest, taking roughly 25 days. The higher latitudes lag behind, out to something like 35 days near the poles. This is called differential rotation, and it is not a curiosity. It is the engine that winds up the Sun's magnetic field, tangles it, and eventually forces it to break through the surface as sunspot regions in the first place. The thing that made active region 4513 is the same thing that is now carrying it across our field of view. Active region 4513 sits at about 3 or 4 degrees north of the solar equator. That is low latitude in the fast lane. At that latitude, the apparent rotation rate, as seen from Earth, is approximately 13.2 degrees per day. That word apparent is doing real work. There are two ways to measure the Sun's rotation. The sidereal rate is how fast it turns relative to the fixed stars. The synodic rate is how fast it appears to turn from where we are standing, and because Earth is also moving around the Sun in the same direction, we are chasing the rotation slightly. The synodic period, the one that actually governs when a region faces us, is a little over 27 days for a full turn. 13.2 degrees a day. That is the number. Now let us apply it. The solar region summary had active region 4513 at east 81 degrees as of midnight on the 19th. By the time the Space Weather Prediction Center issued its forecast discussion at 12:15 Universal Time on the 20th, the region was reported at North 4 East 66. Run the clock forward from there and you get a schedule. Today, the 21st, it is somewhere around East 53. Tomorrow, the 22nd, around East 40. On the 23rd, around East 27. The 24th, East 13. On the 25th of August, it crosses the central meridian, the line straight down the middle of the Sun as we see it, pointed directly at Earth. The 26th, it is at West 13. By the 28th, West 40. By the 30th, around West 66. Why does any of that matter? Because a coronal mass ejection does not steer. When a region erupts and throws off a cloud of magnetized plasma, that cloud travels broadly outward from where it launched, expanding as it goes. From the eastern limb, that vector points across Earth's orbit, off to the side into nothing. It is not that the cloud missed. It was never on a path that included us. That is the entire reason the M8.1 was a non-event for this planet, despite being the largest flare in months, and it is why yesterday's story was about geometry rather than about damage. So there is a band of solar longitude from which an eruption actually travels down the Sun-Earth line. Roughly speaking, it runs from about 30 degrees east to about 30 degrees west of centre. A CME launched from inside that band arrives at Earth as what is called a halo event, expanding toward us so that it appears to spread out in all directions around the Sun in coronagraph imagery, like a ring, because it is coming straight at the camera. The instrument that catches those events is called a coronagraph, and it works by putting a solid disk in front of the Sun to create an artificial eclipse, blocking the overwhelming glare of the surface so that the faint corona around it becomes visible. Without one, you cannot see a coronal mass ejection at all. The cloud is 1,000,000 times dimmer than the disk it came from. Halo events have a specific problem attached to them, and it is one of the genuine limitations of the whole warning system. A coronagraph sees the sky in 2 dimensions, a cloud expanding toward you and a cloud expanding directly away from you, out the back of the Sun, Both appear as a ring spreading outward around the occulting disk. They can look nearly identical. Working out which one you are looking at requires cross-referencing where on the disk the eruption originated, which is why the position of the source region is not a detail. It is the thing that tells you whether the ring in the image is a warning or a curiosity. Active region 4513 enters that band on approximately the 23rd of August and leaves it on approximately the 27th. That is the strike window, 4 to 5 days starting the day after tomorrow. But there is a second window, and it works on a completely different principle, and most coverage of solar storms never mentions it. The sun's magnetic field does not radiate straight outward. The sun is rotating while it emits, so the field lines get dragged into a spiral, in exactly the way water from a rotating garden sprinkler leaves a curved trail in the air even though every individual droplet travels in a straight line. That spiral is called the Parker spiral, after Eugene Parker, who worked it out in the late 1950s. The story of that idea is worth 30 seconds, because it is a useful reminder about how confident consensus can be while being wrong. In 1958, Parker submitted a paper arguing that the sun's outer atmosphere is not static, but is continuously boiling off into space as a supersonic wind, and that this wind drags the solar magnetic field into a spiral. 2 referees rejected it. The prevailing view was that interplanetary space was essentially empty and quiet, and the notion of a permanent wind blowing off the sun struck reviewers as unphysical. The paper was only published because the editor of the astrophysical journal, Subramanian Chandrasekhar, overruled them. 4 years later, in 1962, the Mariner 2 probe flew to Venus carrying instruments that measured the interplanetary medium continuously along the way. It found a solar wind. It was blowing constantly, it was supersonic, and it behaved essentially the way Parker had said it would. The referees had been unanimous and they had been wrong, and the structure they rejected is now the single most important thing to understand about where solar particles actually go. Charged particles do not travel in straight lines through space. They follow magnetic field lines. So when a flare accelerates protons to a substantial fraction of the speed of light, those protons do not go where the flare was pointing. They go where the field line was pointing, and because of the spiral, the field lines that connect most directly to Earth do not come from the centre of the sun's disk. They come from the western side, roughly 50 to 70 degrees west. Active region 4513 reaches that longitude band around the 29th to 30th of August. So there are 2 separate hazards on 2 separate clocks. The cloud of plasma, which drives the geomagnetic storm, has its best shot at us between the 23rd and the 27th. The energetic protons, which are a radiation hazard rather than an electrical one, have their best shot around the 29th and 30th. Different physics, different windows, about 3 days apart. Now, I want to be careful here, and I want you to hold on to the caveats as tightly as you hold the dates. Solar rotation varies with latitude, and the values I have given are approximate. Active regions are not fixed objects. They grow, they decay, they fragment, they merge. The overwhelming majority of regions that look energetic when they rotate onto the eastern limb are considerably quieter by the time they reach the middle of the disk, because most sunspot groups peak early and spend the rest of their transit falling apart. The strike window is a band, not an appointment, and NOAA is not forecasting anything to happen. I want to state their actual position clearly, rather than paraphrase it into something scarier. Their assessment for the 20th through the 22nd is solar activity at low levels, with a chance for isolated M-class flares. Radio blackouts of R1 to R2 at 30% per day, R3 or greater at 5%. Solar radiation storms of S1 or greater at 5%, and no G1 or greater geomagnetic storms expected at all. The greatest observed 3-hour KP index in the previous 24 hours was 3, which is below the threshold where NOAA's storm scale even begins. The greatest expected value through the 22nd is 4, which is also below it. By every operational measure available right now, this is quiet. Here is the tension that makes this worth an hour of your time. The forecast describes the next 72 hours, and forecasts of solar activity beyond about 3 days are, frankly, not much better than climatology. The geometry describes the next week, and the geometry is not a forecast at all. The sun will rotate 13.2 degrees today, and tomorrow, and the day after. That part is not probabilistic. It is arithmetic. So what we actually have is a region that has escalated for 2 days, whose true magnetic complexity is currently unmeasurable, whose first honest measurement arrives around the 22nd or 23rd, and which enters the position where its eruptions would reach Earth on the 23rd. The measurement and the window open on the same day. We will find out what this thing is at approximately the moment it stops mattering whether we know. And if it does fire while it is facing us, the thing that arrives is not one event. It is 4 of them, travelling at 4 different speeds, and only one of them arrives slowly enough to do anything about. Part 4. 8 minutes and 20 seconds. Light takes 8 minutes and 20 seconds to travel from the Sun to the Earth. That number is the entire warning time for the first thing that arrives. Not 8 minutes to prepare. 8 minutes and 20 seconds between the event happening and the event being detectable. Which is the same as saying there is no warning at all because nothing that detects the flare can act any faster than the flare itself is travelling. The photons that carry the news and the photons that do the damage are the same photons. Everything I am about to describe is a projection. I want to be unambiguous about that, because the line between explaining a mechanism and predicting an outcome is exactly where this kind of coverage usually goes wrong. NOAA is not forecasting an Earth-directed event. There is no watch, no warning, no alert. What follows is what the physics says would happen if active region 4513 produced an X-class flare with a fast halo coronal mass ejection while sitting inside the strike window between the 23rd and the 27th. It is a conditional. Hold it as a conditional. So, the flare goes off. What actually reaches us first? X-rays and extreme ultraviolet radiation travelling at the speed of light, arriving after those 8 minutes and 20 seconds, striking whichever half of the Earth happens to be facing the Sun at that moment. And they do something very specific when they get here. The upper atmosphere is not uniform, it is layered, and the layers behave differently depending on how much energy is being pumped into them. The lowest layer of the ionosphere, sitting roughly 60 to 90 kilometers up, is called the D region. Under normal conditions, it is only weakly ionized, and it is thin enough that radio waves pass through it without much trouble. A sudden flood of hard X-rays changes that in seconds. The radiation strips electrons from the neutral atoms down there, and the D region turns from a thin, mostly transparent layer into a dense, conductive one. To understand why that is a problem, you need to understand how long-distance radio has worked for the last 100 years. High-frequency radio, the band from roughly 3 to 30 megahertz, does not travel in straight lines to its destination. It cannot. The Earth curves, and a signal aimed at the horizon just keeps going into space. What makes it work is that the upper layers of the ionosphere, the E and F regions above 100 kilometers, refract those signals and bend them back toward the ground. The signal goes up, bends over, comes down hundreds or thousands of kilometers away, bounces off the surface and goes up again. That is how a transmitter in one hemisphere reaches a receiver in another with no infrastructure in between. No satellites, no cables, no towers, just a wave and a ceiling. A flare does not damage the ceiling. It ruins the floor. When the D region becomes strongly ionized, it stops being transparent and starts absorbing. The signal going up loses its energy in that layer before it ever reaches the reflecting altitude. Nothing bends over, nothing comes back down. The band does not get noisy or degraded. It goes silent across the entire sunlit hemisphere within minutes. That is a radio blackout, and NOAA grades it on a scale from R1 to R5. The M8.1 on the 20th produced an R2, moderate, limited blackout of high-frequency radio on the sunlit side, loss of contact for tens of minutes, degraded low-frequency navigation signals for about the same duration. An X-class flare of the kind we are discussing would produce an R3 or higher, a wide-area blackout, loss of high-frequency radio contact for roughly an hour or more across the entire daylit face of the planet, and navigation signal degradation for hours. Here is the part that makes an R3 concrete rather than abstract. Almost nobody notices it. Your phone will work, your internet will work, your television will work. None of those systems depend on bouncing signals off the ionosphere. What depends on it is a specific and largely invisible set of people, aircraft flying transoceanic and polar routes, where high-frequency radio is the primary means of contact with air traffic control, because there are no ground stations under the North Pole and no cell towers in the middle of the Pacific, ships at sea beyond the reach of coastal systems, emergency and disaster response teams operating in terrain where the infrastructure is either absent or destroyed, which is precisely when they need to talk to each other most, amateur operators, who are frequently the ones relaying traffic in and out of disaster zones during the window before anything else is restored. For all of those people, an R3 is not an inconvenience. It is an hour or more of not being able to reach anyone, arriving without warning, because there was never any warning to give. There is a second effect from the same burst of radiation, and this one does reach into everyday life, though most people who experience it never work out what happened. Satellite navigation signals from the constellations overhead have to pass down through the ionosphere to reach your receiver, and the speed at which they travel through it depends on how many free electrons are sitting in the path. Garnish the atmosphere suddenly and unevenly, and you change that count sharply and irregularly across the whole daylit hemisphere. A navigation receiver calculates your position by timing those signals with extraordinary precision. Change the delay unpredictably and the timing is wrong, and the position that comes out the other end is wrong with it. The high-grade receivers used in surveying, agriculture, aviation, and maritime navigation compensate by using multiple frequencies and correction services, and those systems work extremely well right up until the disturbance is large enough and fast enough that the corrections themselves cannot keep up. That is a failure mode worth sitting with, because it is not a clean one. A navigation system that stops working tells you it has stopped working. A navigation system that is quietly off by a few meters and drifting does not. It keeps producing confident answers that happen to be wrong, and everything downstream of it keeps acting on those answers. Hold that distinction, because it comes back later in this video in a form that cost a great deal of money. That is Layer 1. Layer 2 is already on its way. A large flare does not only emit radiation, it accelerates matter. The same magnetic reconnection that dumps energy into the corona also accelerates protons and heavier ions to a substantial fraction of the speed of light, and those particles then leave the sun and travel outward through the interplanetary medium. Except they do not travel outward in the direction the flare was pointing, and this is where the Parker spiral from earlier stops being a piece of physics trivia and starts being the thing that decides who gets hit. Charged particles cannot cross magnetic field lines easily. They spiral along them. So a proton accelerated at the sun goes wherever the field line it is sitting on happens to go, and the field lines that connect to Earth trace back to the western side of the solar disk, around 50 to 70 degrees west. If the source region is well connected along that spiral, the first protons arrive within tens of minutes. If it is poorly connected, the particles have to diffuse across field lines to reach us, and the event is weaker and slower, or it never really arrives at all. That is the whole reason the proton window for active region 4513 sits around the 29th and 30th of August, several days after the window for the plasma cloud. Same region, same eruption, physics, completely different geometry. NOAA grades this on the S scale, and what it costs is different in kind from a radio blackout. At the lower end, satellites start logging what are called single event upsets. A high-energy proton passes through a memory cell or a logic gate and flips a bit. Most of the time the error correction catches it and nothing happens. Occasionally it does not, and a spacecraft does something unexpected. Star trackers, the cameras that spacecraft use to determine their orientation by looking at known star patterns, start filling with false points of light as particles strike the detector, and a spacecraft that cannot identify which way it is pointing has a real problem. Then there is radiation dose. The atmosphere and the magnetic field between you and space are extremely effective shielding at the surface and at low latitudes, but both of those protections thin out as you go up and as you go poleward, because the field lines that funnel particles down converge near the poles. A commercial aircraft on a polar route during a strong proton event is in the worst combination of both: high altitude, high latitude. During the Halloween storms of 2003, airlines responded by diverting polar flights to lower latitudes, which costs fuel, costs time, and in some cases means the route cannot be flown at all. At the extreme end, and this is where the honesty matters more than the drama, a severe proton event is a genuine hazard rather than an operational nuisance for anyone who happens to be outside Earth's shielding altogether. That is a small number of people. It is not zero. So run the two layers together and look at what you have. An X-class flare from a region facing us produces a planet-wide radio blackout on the daylit side that arrives at the speed of light, and a radiation environment that begins degrading spacecraft and exposing polar flights within tens of minutes. For both of those, the forecast and the event are simultaneous. Every warning system, every alert, every advisory, every piece of the infrastructure built over decades to protect against this is useless against the first two layers, because information cannot outrun the thing it is describing, and neither of those layers is the one that does the real damage. The thing that breaks transformers, the thing that costs hundreds of billions of dollars, the thing that keeps grid operators awake, is still out there, moving at a small fraction of the speed of light, hours or days behind. Part 5. The slow part. The light already arrived. The cloud is still coming, and the cloud is the part that matters. A coronal mass ejection is not a beam or a burst, it is an object, a structure of magnetized plasma, typically containing something on the order of 1 billion tons of material, torn out of the sun's outer atmosphere and thrown into space as a coherent thing that holds together across 150 million kilometers. It carries its own magnetic field, wound up inside it in a rope-like configuration, and that internal field is going to turn out to be more important than its mass or its speed. We have a measurement of how fast the one on the 20th was moving, and the way we got it is one of the more elegant tricks in the field. When the M8.1 went off, it produced what is called a Type 2 radio sweep, with an estimated velocity of 1,201 km per second. A Type 2 sweep is not an image of anything. It is a sound, in effect. As a shock front drives outward through the corona, it excites the plasma it passes through, and plasma emits radio at a frequency set by its density. The corona thins out with altitude, so as the shock climbs, the emission it triggers drifts steadily downward in frequency. Plot that drift against time. Apply a model of how coronal density falls off with height, and the slope gives you the speed of the shock. You measure the velocity of something you cannot see by listening to the frequency of a noise it makes on its way out. 1,201 kilometers per second. Let us work out what that means. The distance from the Sun to the Earth is about 149.6 million kilometers. Divide that by 1,201 kilometers per second, and you get roughly 124,500 seconds, which is about 34.5 hours. That is the constant velocity answer, and it is wrong, but usefully wrong. Real coronal mass ejections do not hold their launch speed. They are moving through the ambient solar wind, which in current conditions is running at around 550 kilometers per second, and anything travelling faster than the medium it is in decelerates against it. A cloud launched at 1,200 kilometers per second typically arrives somewhere between 40 and 50 hours later. The fastest events on record have crossed in under 20 hours. Slow ones take 3 or 4 days, call it a day and a half. That interval, that roughly 36 to 50 hour gap between the flash and the arrival, is the single most valuable thing in this entire field. Every satellite, every model, every forecaster, every operational procedure in space weather exists to convert that gap into something useful, and it genuinely is useful. Given a day and a half of notice that a significant storm is inbound, grid operators can reduce loading on vulnerable transmission paths, bring reserve generation online so the system is not running close to its limits, and postpone maintenance that would take redundant capacity out of service. Satellite operators can put spacecraft into safe modes, suspend orbit-raising maneuvers, and delay launches. Airlines can plan reroutes rather than improvise them mid-flight. Pipeline operators can hold off on inspection procedures that are sensitive to induced currents. None of that stops a storm. All of it changes how much a storm costs. But there is a catch, and it is a serious one. Knowing that a cloud is coming is not the same as knowing what it will do when it gets here, and the difference between a spectacular aurora and a continental emergency comes down to the orientation of a magnetic field inside a cloud you cannot measure until it is nearly on top of you. Earth has a magnetic field. It points broadly northward through the region where the incoming plasma arrives. If the magnetic field embedded in the coronal mass ejection also points northward when it hits, the two fields are aligned, they resist each other, and most of the energy in the cloud slides around the magnetosphere and continues past. You get a compression, some disturbance, and not much else. If the cloud's field points southward, the two fields are anti-parallel, and something quite different happens. Opposing magnetic fields in contact undergo reconnection. They break and reattach into a new configuration, and in doing so they open a pathway that lets energy and plasma from the solar wind pour into the magnetosphere instead of flowing around it. Energy loads into the magnetotail on the night side, builds and then releases in bursts that drive electrical currents through the upper atmosphere at high latitudes. Those currents are what produces the aurora, and those same currents are what produces everything that happens on the ground afterward. The southward component of the interplanetary magnetic field is written as BE, and it is not an exaggeration to say that B decides the outcome. The same cloud, at the same speed, with the same mass, arriving with a northward field instead of a southward one, is a fundamentally different event. Here is the problem. You cannot reliably measure B's remotely. You have to fly through the cloud. The measurement comes from spacecraft parked at a point called L1, about 1.5 million kilometers upstream of Earth, on the line toward the Sun, where the gravitational pull of the two bodies balances in a way that lets a satellite hold station. Those spacecraft sample the solar wind as it passes them on its way to us. At typical solar wind speeds, 1.5 million kilometers of lead translates to somewhere between 15 and 60 minutes. That is a very small amount of infrastructure to hang a planet's warning system on. A handful of spacecraft sitting at a single point, several of them well past their design lifetimes, measuring a cloud that is about to hit us by the crude expedient of being hit by it first. There is no second line. If those instruments are not working, or if the cloud happens to strike a part of the front that misses them, the 15 to 60 minutes goes away and you find out what the storm is when the ground tells you. It is also worth being honest about how good the day and a half of notice actually is, because the arrival time itself is not precisely known either. Predicting when a coronal mass ejection will reach Earth means modelling how a structure of unknown internal density decelerates through a solar wind whose speed and density vary along the way. The models are genuinely impressive, and they are still routinely off by several hours in either direction. An operator planning around a predicted arrival is planning around a window, not a moment. And then there is what happens at the instant of arrival, before any of the ground effects begin. The leading edge of a fast cloud is a shock front, and when it hits the magnetosphere it compresses it, hard. In a strong enough event, the boundary of Earth's magnetic field, which normally sits around 10 Earth radii out on the sunward side, can be pushed inside geosynchronous orbit. Satellites that spend their entire operational lives inside the protection of the magnetosphere suddenly find themselves outside it, exposed directly to the solar wind in an environment they were never specified for. So the real structure of the warning is this. You get a day and a half of notice that something is arriving. You get 15 to 60 minutes of notice about how bad it is going to be. Everything an operator does in that day and a half is done without knowing whether the storm will be trivial or historic, which means preparing for a severe event that turns out to be minor has a cost, and not preparing for one that turns out to be severe has a much larger one. It is worth separating two kinds of geomagnetic storm here, because they get reported with the same vocabulary and they are not the same event. What I have been describing is a storm driven by a coronal mass ejection, a discrete cloud arriving at a specific time, hitting hard and passing through within a day or two. The other kind is driven by a high-speed stream where the solar wind flowing out of a gap in the sun's magnetic field catches up with slower wind ahead of it and piles into a compression region that sweeps past Earth as the sun rotates. High-speed stream storms are gentler and far more persistent. They rarely produce the severe end of the scale, but they can keep a magnetosphere disturbed for days at a stretch, and because they are tied to a feature that survives multiple solar rotations, they tend to come back on a 27-day rhythm. The distinction matters for what comes later in this video, because Earth is currently sitting in exactly that kind of stream, and it has been for days. Right now, for the record, the numbers coming back from upstream are quiet. Solar wind around 550 kilometers per second, elevated but unremarkable, and elevated for precisely that reason. A coronal hole stream, not an eruption. Total magnetic field strength around 5 nanotesla. BZ oscillating between plus and minus 5, which is to say wandering back and forth across zero without committing to anything. That is a calm interplanetary medium. Nothing in those readings is a warning. None of the physics in this part is specific to active region 4513. Every coronal mass ejection works this way. What is specific to this region is that within days it will be standing in the one place on the Sun from which the cloud comes at us rather than past us. And when the cloud arrives and the field couples and the currents begin to flow, the story stops being about space entirely. It comes down to the ground, into equipment, into buildings, into machines that were never designed with any of this in mind. Part 6. The ground and the air. The most expensive consequence of a solar storm happens inside a large grey box sitting in a fenced yard on the edge of a town, and almost nobody has ever looked at one closely. The chain that gets us there starts in the upper atmosphere. When a coronal mass ejection couples to Earth's magnetic field, it drives enormous electrical currents through the ionosphere at high latitudes in a structure called the auroral electrojet. Those currents are not metaphorical. They are millions of amperes flowing through the upper atmosphere, and they vary rapidly as the storm develops. A changing electrical current produces a changing magnetic field. A changing magnetic field passing through a conductor induces an electric field inside it. That is Faraday's law, discovered in 1831, and it is the same principle that runs every electrical generator on the planet. The conductor in this case is the Earth itself. The rock beneath your feet conducts, poorly but measurably, and a storm overhead induces a geoelectric field in the ground across whole regions at once. An electric field in the ground drives current through anything that offers an easier path than the rock does, which means anything long, metallic, and connected to the Earth at both ends. Transmission lines, pipelines, railway signalling circuits, the power conductors inside undersea cables. These induced flows are called geomagnetically induced currents, and the amount you get depends heavily on what the ground under the line is made of. Highly conductive sediment absorbs the current itself. Ancient resistive igneous rock does not, and forces it up into whatever infrastructure is bolted to the surface. That single fact means the hazard is not distributed evenly across a country or even across a state. Two substations a few hundred kilometers apart, connected to the same grid, experiencing the identical magnetic disturbance overhead, can see wildly different induced currents purely because of what is under them. The geological map is a risk map, and it does not resemble the population map or the infrastructure map at all. There is a particular amplifier worth knowing about, because it puts a surprisingly large fraction of the world's infrastructure in the wrong place. Seawater is a good conductor. Continental bedrock frequently is not. At a coastline, you have those two materials meeting along a sharp boundary, and the induced currents flowing easily through the ocean pile up where the conductivity drops. The result is that the geoelectric field gets locally intensified along coastal margins. This is called the coast effect, and it means that the places where the geoelectric hazard is amplified are, as a matter of historical accident, exactly the places where humans built their largest cities, their densest grids, and the landing points of every undersea cable in the world. Now, the transformer. Every high-voltage transformer works on alternating current. The current reverses direction 50 or 60 times a second depending on where you live, and the magnetic core inside the transformer flips its magnetization back and forth in step, cycling symmetrically around zero. The whole design assumes that symmetry. A geomagnetically induced current is quasi-direct. It flows one way and it changes over minutes rather than milliseconds, which as far as a 60 Hz transformer is concerned is effectively constant. Inject that into the winding, and you add a steady bias to the magnetization. The core no longer cycles around zero, it cycles around an offset. The consequence is called half-cycle saturation. On one half of every cycle, the core is pushed past the point where it can hold any more magnetic flux. Iron saturates. Once it does, it stops behaving like a transformer core and starts behaving like empty air, and the magnetic flux that should be neatly contained inside the core spills out into everything nearby. The windings, the clamping structures, the steel of the tank itself. Two things follow. The current the transformer draws to magnetize itself distorts badly, and that distortion propagates through the network as harmonics, which is what trips protective relays and can knock out capacitor banks and other equipment that has nothing directly wrong with it. And stray flux dumps energy as heat into metal parts that were never intended to carry any. This is where the thermal argument becomes the whole story. An extra high voltage transformer is designed to run continuously for 30 or 40 years inside a fairly narrow temperature envelope, with its insulation degrading slowly and predictably across that entire span. Localized hotspots that would be harmless for a few seconds are a very different proposition sustained over the tens of minutes that a storm's main phase can last. Insulation cooks, oil degrades, and unlike almost every other failure mode in a power system, it can happen while every meter in the control room still reads normal because the damage is thermal and internal and takes time to show up. There is a second failure path that does not require damaging anything, and it is faster and in some ways more dangerous. A saturated transformer draws far more reactive power than a healthy one, and reactive power is what holds the voltage up across a network. Meanwhile, the harmonics being injected are exactly the thing that trips capacitor banks offline, and capacitor banks are one of the main tools for supplying reactive power. So the storm simultaneously increases the demand for voltage support and destroys the means of providing it. Push that far enough, and the voltage across a region falls faster than anything can respond, and the system collapses to protect itself. Nothing has broken. Everything has stopped. To understand why the other path matters so much, it helps to know what one of these machines physically is. An extra high voltage transformer is not an appliance. It is a custom-engineered object, frequently weighing hundreds of tons, built to the specifications of one position in one network. They are not interchangeable and they are not stocked in warehouses. They are moved by rail on purpose-built cars or by road on transporters that require route surveys and bridge assessments months in advance. The manufacturing lead time is measured in months, and the number of facilities worldwide capable of building the largest units is small. So there are two possible outcomes when a big storm hits a transformer, and the entire economic range of a solar storm scenario lives in the gap between them. Either the protective systems detect the harmonics and trip the unit offline, in which case you have lost capacity but you have not lost equipment, and you can re-energize in hours once the storm passes, or the insulation is damaged and the unit is not coming back at all. Back on the 12th of August, we looked at how a total eclipse functions as a stress test for a grid, pulling gigawatts of solar generation offline along a predictable path at a predictable moment. Operators handle it, and they handle it well, because they know precisely when it starts, precisely where the shadow goes, and precisely how long it lasts. This is the same physical system meeting the opposite kind of stress, unscheduled, unbounded, and hitting every part of the network at once, instead of sweeping across it in a line. There is a fifth layer, and it is the quietest one, and it may end up being the most consequential. When a storm dumps energy into the upper atmosphere, the atmosphere heats. Heated gas expands, and because there is no lid on the top of the atmosphere, it expands upward, which means the density at any given altitude goes up, sometimes dramatically. Satellites in low Earth orbit are flying through the top of the atmosphere. It is extremely thin up there, but it is not nothing, and over months and years the drag from it is what eventually brings every low-orbiting object down. Raise the density suddenly and you raise the drag on every object in that altitude band simultaneously. Orbits decay faster than predicted. Spacecraft that were where the models said they would be yesterday are somewhere else today. That has two consequences, and the second is worse than the first. Individual satellites lose altitude and have to spend fuel recovering it, which shortens their operational lives. But more importantly, every prediction about where anything is going to be becomes unreliable at the same moment, for thousands of objects at once in a region of space that is now more crowded than it has ever been. The organizations that track objects in orbit do it by maintaining a catalogue, and a catalogue entry is not a photograph. It is a model, fitted to past observations, propagated forward to say where the object should be tomorrow. Those models include a term for atmospheric drag, and that term is calibrated against normal conditions. Change the density of the atmosphere by a large factor over the course of a few hours, and every propagated position in the catalogue is now wrong, and wrong by different amounts depending on each object's altitude, shape and mass. Getting the catalogue back means re-observing objects, matching them to their old identities, and refitting the orbits. With a handful of satellites that is straightforward. With tens of thousands of tracked objects, many of them small pieces of debris that look identical to each other, it is a substantial and slow undertaking. The tracking does not fail dramatically. It degrades quietly for days, and during that degradation the entire basis for knowing whether two objects are about to hit each other is weaker than anyone would like. Which brings us to the point of all of this. 5 layers, from radiation that arrives in 8 minutes to atmospheric expansion that plays out over days. One eruption from one region that will be in position to deliver all of it within days. Everything I have described in this act is a model. Careful, well-established, built on solid physics, and still a model. So it is worth asking what has actually happened in the real world when storms like this have actually arrived. Because the record is not reassuring, and the most instructive event in it is not the one you would expect. Part 7. 57 seconds. On the morning of the 1st of September, 1859, an English astronomer named Richard Carrington was doing what he did most clear mornings, which was projecting an image of the sun onto a screen in his private observatory and carefully sketching the sunspots. At around 11:18, 2 points of intensely bright white light appeared within the sunspot group he was drawing. He assumed at first that a hole had opened somewhere in his equipment and that he was seeing unfiltered sunlight leaking through. It was not that. The 2 points brightened, moved across the group over the course of about 5 minutes and faded. Carrington ran to fetch someone else to confirm what he was seeing, and by the time he got back it was nearly over. He had just become the first human being to observe a solar flare, and it was an enormous one. He was not the only one. An amateur astronomer named Richard Hodgson, observing separately, saw the same brightening, which is why we can be confident it was real and not an artefact of one man's equipment. And there was a third witness, which is in some ways the most important of the three because it was not a person at all. At the Kew Observatory outside London, a magnetometer was continuously recording the strength of Earth's magnetic field on a moving photographic plate. At the moment Carrington was watching those 2 white points, the Kew instrument recorded a sharp disturbance in the terrestrial magnetic field. That disturbance is what we now call a magnetic crochet, and it is caused by the flare's X-rays ionizing the upper atmosphere and altering the currents flowing there. It arrives with the light, in 8 minutes and 20 seconds, which is why it showed up while Carrington was still sketching, 17 hours before the main storm. Nobody at the time could have explained any of it. X-rays would not be discovered for another 36 years. The idea that the sun could throw material across interplanetary space was a century away from acceptance. What they had was a bright light on the sun, a needle jumping in a London observatory, and then, a day later, the ski on fire. What happened next is the reason we still talk about it. Within hours, the aurora began. It was seen across Europe and North America, and then it kept going, further and further from the poles, until it was visible in the Caribbean. There are accounts of people in the tropics being woken by a red glow through their windows and assuming a city was burning. There are accounts of gold miners in the American West getting up and starting breakfast, because the light was bright enough that they assumed it was dawn, and the telegraph networks failed. This is the detail that gives the Carrington event its real weight, because it is the first time in history that a solar storm reached down and touched human infrastructure. Telegraph operators across Europe and North America reported sparking at their equipment. Some received electric shocks. Some found that their systems continued to transmit and receive after they had disconnected their batteries entirely, running on the current the storm was inducing in the lines. Paper caught fire at some stations, others simply went dead. Now think carefully about what that infrastructure actually was. Wires strung on poles, a battery, a key, and a sounder. That is a telegraph network. It is the simplest electrical system humanity has ever built at scale, with no semiconductors, no transformers, no automated protection, no interdependency with anything else. There was almost nothing there for a solar storm to damage, and it damaged it anyway. That is the reference ceiling. Everything since has been measured against a storm that hit a civilization which had essentially no electrical exposure and disrupted it regardless. Now come forward 130 years. At 2:44 in the morning on the 13th of March, 1989, the Hydro-Quebec power grid in eastern Canada was operating normally. A geomagnetic storm had been underway for hours, driven by a coronal mass ejection that had left the sun days earlier. Induced currents were flowing through the long transmission lines that carry power south from the hydroelectric stations of James Bay to the population centres near the St. Lawrence. What happened over the next minute is the most studied grid failure in the history of space weather. 7 separate failures occurred on the grid within 57 seconds. The saturating transformers were injecting harmonics into the network. Those harmonics tripped the static compensators at the Chibougamau substation offline, one after another. With the compensators gone, the reactive power support that was holding the voltage up on the James Bay transmission corridor disappeared. Voltage collapsed across the network faster than any operator could have responded to, faster than most automated systems could respond to, and the entire Quebec grid went down. 57 seconds. From a functioning power system to a dark province. Approximately 6 million people lost power for around 9 hours in Quebec in March. Schools and businesses closed, the Montreal metro stopped, the airport shut down. And this was not confined to Canada. The same storm damaged a high-voltage transformer at the Salem Nuclear Generating Station in New Jersey, hundreds of kilometers away on a completely different grid, in a different country, under different management. Here is the correction that turns 1989 from a reassuring story into an unsettling one, and it is the thing most retellings leave out. That was not a Carrington-class event. It was not close. It was a strong storm, a serious one, but it sits well down the scale from what the Sun is known to be capable of. What made it catastrophic was not the size of the storm. It was that it hit a grid which had never been designed with geomagnetic currents in mind, in a place where the geology was working against it. Quebec is built on the Canadian Shield, some of the oldest and most electrically resistive rock on the planet. Induced current flowing through the ground hits that shield and finds the transmission lines a far easier path than the bedrock. Add to that the geometry, very long lines running roughly north to south at high geomagnetic latitude, directly under the auroral electrojet. If you set out deliberately to design a power system that would maximize its own exposure to geomagnetically induced currents, you would arrive at something that looked a great deal like the one that was serving Quebec in 1989. The lesson is not that the storm was extraordinary. The lesson is that a merely strong storm found the one system that was maximally vulnerable to it, and took that system down in under a minute. What happened afterward is the part of the story that should give you some comfort, and it is worth including because this video is not an argument that nothing can be done. Hydro-Quebec responded by rebuilding. They installed series compensation on the James Bay corridor, changed protective relay settings so that harmonics from a geomagnetic event would not trip the compensators the way they had, and put in monitoring specifically to watch induced current levels in real time. The utility that took the worst hit in the modern record is now among the better prepared operators anywhere. The broader industry moved too, though more slowly. 1989 is the reason geomagnetically induced current monitoring exists as an operational discipline at all. The reason regulators eventually began requiring grid operators to assess their vulnerability to geomagnetic disturbance, and the reason there are now published operating procedures for what to do when a storm warning arrives. None of that existed before a province went dark in 57 seconds. So the honest picture is not that we learned nothing. It is that we learned from a storm well below the ceiling, and the improvements were sized against the storm we experienced rather than the one the Sun is capable of producing. Then there is October and November of 2003, in a period now known as the Halloween storms. The Sun produced an extraordinary run of activity, an X-17 flare on the 28th of October, and then on the 4th of November, an event so large it saturated the sensors measuring it, later estimated at X-28 or greater, which remains the largest flare in the instrumental record. To put that next to the events in this video, the M8.1 on the 20th of August was roughly 1/300th the intensity of that flare. The consequences were spread across every domain we have discussed. Transformer and grid problems in Sweden produced a blackout in Malmö, lasting around an hour. Airlines rerouted polar flights away from high latitudes at considerable operational cost. Satellites logged anomalies across the fleet, some losing instruments permanently. Ground systems reported navigation degradation. Astronauts aboard the space station moved to the most shielded part of the vehicle. But the detail I want to leave you with about the Halloween storms is not any of that. It is when they happened. Solar cycle 23 reached its maximum in the year 2000. The Halloween storms occurred in late 2003, more than 3 years after that peak, on the declining side of the cycle, at a point when the number of sunspots had been falling for years, and any reasonable person looking at the trend would have concluded the dangerous part was over. Solar cycle 25 reached its maximum in October of 2024. We are 22 months past it. We are on the declining side. The sunspot numbers are coming down and the overall rate of activity is falling, and every one of those statements is true, and none of them means what people instinctively assume they mean. The frequency of events declines after maximum. The severity of the largest possible event does not decline with it, and the historical record keeps putting the worst storms in exactly the phase we are in now. Which brings us to the most instructive event of the modern era, and it is not any of the three I have just described. It did not come from a great flare or a famous storm. It came from something so small that nobody issued a serious warning about it at all. Part 8. 38. Satellites. On the 3rd of February 2022, SpaceX launched 49 Starlink satellites into low Earth orbit. Within days, 38 of them were gone. The storm that destroyed them was classified as minor, not extreme, not severe, not even strong. Minor, which sits at the bottom of the geomagnetic storm scale, the category that produces auroras visible from high latitudes and essentially nothing else. The kind of disturbance that happens dozens of times a year and gets a single line in a forecast discussion. That is what took out 3/4 of a launch. Here is how, step by step, because the mechanism is the whole point. Starlink satellites are deployed into a deliberately low initial orbit. The batch launched on the 3rd of February went into an orbit with an apogee of around 350 kilometers and a perigee of around 210. That is very low, and it is low on purpose. If a satellite fails its post-deployment checks at that altitude, atmospheric drag pulls it down within weeks and it burns up rather than becoming debris. Healthy satellites raise themselves to their operational altitude of around 550 kilometers using onboard thrusters over the following days. It is a sensible design. It puts the satellites through a brief window of vulnerability in exchange for a guarantee that failures clean themselves up. The geomagnetic storm arrived during that window. Energy deposited into the upper atmosphere heated it, and the heated gas expanded upward, and the neutral density at satellite altitudes went up sharply. The measured increase was somewhere between 50 and 125% at altitudes between 200 and 400 kilometers. At the 210 kilometer perigee where those satellites were sitting, drag increased by roughly 50%. The response is the human part of the story. The operators recognized what was happening and commanded the satellites into a safe hold attitude, turning them edge-on to the direction of travel to present the smallest possible cross-section, the same instinct as turning sideways in a strong wind. They managed it for 11 of the 49. The other 38 could not overcome the drag. Their thrusters could not raise them faster than the atmosphere was pulling them down. Over the following days they lost altitude, and then they re-entered and burned up. Sit with the shape of that. A minor storm, not a rare event, not an unforecast one either, in the sense that the disturbance had been anticipated in general terms. And it destroyed 38 spacecraft because they happened to be in the one configuration and the one altitude band where a minor storm is a lethal event rather than a footnote. There is an uncomfortable irony buried in it as well. The low deployment altitude was a safety feature. It exists so that a failed satellite comes down quickly and cleanly, instead of lingering as debris in a crowded orbit for years. And it worked exactly as intended. All 38 re-entered and burned up, leaving nothing behind. The design succeeded completely at the thing it was designed for, while the mission failed completely, and both of those statements are true because of the same decision. The event generated a genuine scientific literature. Multiple papers followed in the space weather journals analysing what had happened, and the reason so many researchers converged on one incident is that it was a natural experiment nobody could have run deliberately. A large, identical, well-instrumented set of objects at a known altitude, hit by a well-measured disturbance, with a precisely known outcome. It turned a modelling problem into a measurement, and what it measured was that the models had been underestimating how much the atmosphere responds. That is the part worth carrying forward. The storm was not bigger than expected. The atmosphere's reaction to it was. That is the lesson this entire video has been building toward, so let me state it as plainly as I can. The damage a storm does is not a property of the storm. It is a property of the collision between the storm and whatever state the system happens to be in when it arrives. The same disturbance, a week earlier or a week later, would have been nothing at all. 2 years later, the other half of the lesson arrived, and this time it was a genuinely large storm. In May of 2024, a sequence of eruptions produced the strongest geomagnetic storm to reach Earth in 20 years. It is known as the Gannon storm, and the auroras it produced were seen at latitudes where most people alive had never seen them, which is the part everybody remembers. What happened underneath the light show is more interesting. It was the second week of May, which in the American Midwest means planting season, and modern planting is a satellite navigation operation. Tractors run on guidance systems accurate to a couple of centimetres, using correction signals to steer implements down rows with a precision no human driver can match. The economics of the entire operation assume that precision. The Gannon storm disrupted those signals across 12 Midwestern states that together produce close to a third of the world's corn at the peak of the planting window. The estimated losses to Midwestern crop producers were approximately $565 million, and the way it failed is exactly the failure mode I flagged earlier. Farmers reported that their tractors were behaving, in their words, like they were demon-possessed, not switched off, not showing an error, steering confidently in the wrong direction, wandering off the row, correcting toward positions that were not where the machine actually was. A guidance system that dies tells you it has died, and you stop. A guidance system that is quietly wrong keeps working, and so do you. And by the time anyone notices, the field is planted badly and the season is running out. It is worth understanding why the correction systems fail, because it explains why the most sophisticated equipment fails first. A basic navigation receiver gives you a position accurate to a few meters, and it is not much bothered by moderate ionospheric disturbance, because a few extra meters of error on top of a few meters of error is not a qualitative change. Centimetre-level guidance works by modelling the ionospheric delay precisely and subtracting it, using a nearby reference station or a correction service that assumes the ionosphere varies smoothly across the region between the station and the receiver. During a severe storm, that assumption breaks. The ionosphere stops being smooth and develops sharp, fast-moving structure, and a correction computed for a reference station 40 kilometres away is no longer valid where the tractor is. The correction that normally removes the error starts adding 1, which means the machines that suffered most were the newest and most precise ones on the farm, and a 40-year-old tractor with a human driver watching the row would have planted the field without noticing anything had happened. Aviation saw the same category of failure at a much larger scale. The Wide Area Augmentation System is the network of ground stations that measures satellite navigation errors and broadcast corrections precise enough to guide aircraft down through cloud on an approach. During the storm, it could not keep up, and the service that supports vertical guidance was lost at roughly 2,000 airports across the continental United States and Alaska from the 10th to the 12th of May. Nothing crashed, and nobody was hurt. The system degraded exactly the way it is supposed to degrade, which is to say it withdrew the service rather than continuing to offer a guarantee it could no longer meet, and flights fell back on other approach procedures. But 2,000 airports is not a marginal number, and the fallback procedures generally require better weather, more separation, or more fuel. And then there is what happened in orbit, which is the beat this entire part has been building toward. Modern satellite constellations manage themselves. Station keeping is automated. The spacecraft detects that its orbit is decaying and fires its thrusters to compensate without a human in the loop. That is a sensible design for a constellation with thousands of members, because no operations team could handle that workload manually. When the Gannon storm expanded the atmosphere, every one of those satellites detected orbital decay at the same moment, and every one of them responded the way it was designed to. Close to half of all active satellites in low Earth orbit maneuvered simultaneously. That is thousands of objects, all changing their orbits at once in the same few hours, while the atmospheric density model underlying every prediction about where any of them would be was simultaneously wrong. The result was that conjunction assessment, the process of working out whether two objects are on course to collide, became extremely difficult during the storm and for days afterward. The Gannon storm did not destroy the constellation. It did something stranger and arguably worse. It temporarily blinded the system that keeps thousands of satellites from hitting each other at the exact moment when all of those satellites were moving. And here is the connection back to the region we have been tracking. Neither of these was the kind of event active region 4513 could produce from inside the strike window. February 2022 was a minor storm. May 2024 was strong, and it was the strongest in 2 decades, and it still sits far below the Carrington ceiling and below what the Halloween storms delivered. These are not the worst case. These are the floor. This is what happens when the sun is not really trying. Part 9. The loaded system. Everything I have described so far is either history or projection. Let us talk about right now, because the space environment around Earth at this moment is not in a rested state, and that turns out to matter enormously. For the past several days, Earth has been sitting inside a coronal hole high-speed stream. A coronal hole is a region where the sun's magnetic field, instead of looping back down to the surface, opens outward into space. Along those open field lines, the solar wind is not held back by anything, and it escapes at considerably higher speed than the wind from the surrounding closed field regions. As the sun rotates, that fast stream sweeps around like a jet from a rotating sprinkler head, and when it points at Earth, we sit in it for days. You can see coronal holes directly. In extreme ultraviolet images of the sun, they appear as dark patches, sometimes enormous ones stretching from pole to equator, and they look dark for a straightforward reason. The hot plasma that glows at those wavelengths is normally trapped in closed magnetic loops, and where the field is open, the plasma streams away instead of accumulating. There is nothing there to glow. A coronal hole is a picture of an absence. The current one is described in the forecast as negative polarity, meaning the open field lines point inward toward the sun rather than outward, and that detail is not cosmetic. The polarity of the arriving field interacts with Earth's own field differently depending on its sign and on the time of year, which is why identical streams can produce noticeably different levels of disturbance in different months. Coronal holes also last. Unlike sunspot regions, which emerge and decay over days to weeks, a large coronal hole can persist for several solar rotations, which means the same stream comes back to hit us roughly every 27 days, again and again, until the hole finally closes. Forecasters use that recurrence as one of the few genuinely reliable long-range signals in the field. That is why the solar wind speed is currently running around 550 km per second, rather than the 300 to 400 that is typical of quiet conditions. It is not an eruption, it is a persistent draft, and it has been blowing on us since before active region 4513 produced its first flare. Now here is the number in this entire video that gets the least attention and probably deserves the most. Greater than 2 mega-electron-volt electron flux at geosynchronous orbit was forecast to cross 1,000 particle flux units on the 20th of August, and to remain at high levels through the 21st and 22nd, driven by that high-speed stream. That sounds like instrumentation trivia. It is not. Let me explain what those electrons do. Spacecraft shielding is designed to stop most of what space throws at it. Low-energy particles stop at the skin of the vehicle and deposit their charge on the outer surface, where it can be managed. That is surface charging. It is well understood, and spacecraft are built with conductive coatings and bonding straps specifically to equalize it. High-energy electrons do not stop at the skin. At a few mega-electron volts, they punch through the outer structure and come to rest inside the vehicle, embedded in the insulating materials deep within it. Cable insulation, circuit board substrate, the dielectric layers inside components, materials that were selected precisely because they do not conduct, which means the charge that accumulates there cannot flow away. It just sits and builds as long as the flux stays elevated. Eventually the electric field across that insulator exceeds what the material can withstand, and it breaks down. The charge finds a path through the dielectric and discharges, releasing an electrical pulse inside the spacecraft's electronics, past every layer of protection designed to keep such things out. That is internal charging, and depending on where it happens it can flip a bit, corrupt a command, damage a component, or in the worst cases trigger a fault cascade that ends a mission. The critical property of internal charging is that it is cumulative. It is not a threshold you cross and then survive. It is an accumulation that builds over days of exposure, and a satellite that has been sitting in elevated flux since the 20th of August is in a materially different condition on the 25th than one that has spent the week in a quiet environment. This is not theoretical. In April of 2010, a communications satellite called Galaxy 15 stopped responding to commands from the ground while continuing to transmit, which meant it became an uncontrollable object drifting slowly along the geostationary belt with its transponders still running, threatening to interfere with every satellite it passed. The press nicknamed it the zombie satellite. Investigations pointed to an electrostatic discharge event driven by the space environment as the most likely cause during a period of elevated activity. It took months to recover, and it was recovered only because the spacecraft eventually drained its batteries, reset itself, and could be reacquired. That is what this failure mode looks like when it happens, not an explosion, a spacecraft that stops listening. Now connect that to the Starlink story from a few minutes ago, because these are the same lesson arriving from two directions. Charging is a slow accumulation, a coronal mass ejection arrival is a sudden shock, and the entire point of February 2022 is that a sudden shock landing on a system that is already at a disadvantage does damage completely out of proportion to the size of the shock. That is what preconditioning means, not that a storm is coming, that the ground it would land on is softer than it would otherwise have been. So let me be scrupulous about what the current numbers actually say, because I have just spent several minutes building a case and I do not want to overstate it. The KP index is worth a moment, since I keep quoting it. It is not measured at one place. It is compiled from a network of magnetometer stations distributed around the world, each recording how much the local magnetic field deviates from its normal quiet day behavior over a 3-hour window. Those local deviations get standardized and combined into a single planetary figure on a scale from 0 to 9, and because the scale is quasi-logarithmic, each step up represents a substantially larger disturbance than the one below it. NOAA's geomagnetic storm scale hangs directly off it. KP5 is a G1, minor, KP6 is G2, KP7 G3, KP8 G4, KP9, the top of the scale, is a G5, extreme. The May 2024 Gannon storm reached G5. The March 1989 storm that collapsed the Quebec grid also reached the top of the scale. Everything measurable right now says quiet. The greatest observed 3-hour KP index over the past 24 hours was 3, which is below the level where NOAA's geomagnetic storm scale even starts. The greatest expected value through the 22nd is 4, also below it. NOAA explicitly forecasts no G1 or greater geomagnetic storms. The greater than 10 mega electron-volt proton flux, the one that matters for radiation storms, has been at background levels and is expected to stay there. The rationale in the forecast is blunt. No significant transient or recurrent solar wind features are forecast. By every operational measure, this is an ordinary late August day in near-Earth space. The preconditioning argument is not a claim that something is happening. It is a claim about what a future disturbance would be landing on, and if no disturbance arrives, the argument costs nothing and means nothing. There is also a genuine caveat that cuts against the whole case, and leaving it out would be dishonest. The high-speed stream is forecast to wane. The forecasters describe its influence near Earth as waning through the 22nd. If that holds, the elevated electron flux falls off with it, and by the time the strike window opens on the 23rd, the fleet has had a chance to bleed off accumulated charge, and the loading argument is considerably weaker than it looks today. But notice the asymmetry in the timing, because this is the structural point. The state of the environment builds slowly and visibly. We can watch it for days. We know exactly what the electron flux has been doing, and we have a reasonable forecast for what it will do next. The disturbance itself, the thing that would actually cause harm, gives 40 to 50 hours of notice at the outside, and 15 to 60 minutes of notice about whether it will be serious. One half of the equation is slow and legible, the other half is fast and conditional. And the severity of anything that happens in the strike window is the product of both. So the honest summary of where we stand is this. There are two independent variables, what active region 4513 does, and what condition we happen to be in when it does it. We can watch the second one directly, day by day, and it is currently trending toward quiet. The first one we cannot even measure yet because the region is still too close to the limb to classify, and the first honest reading arrives on the 22nd or 23rd at essentially the same moment the strike window opens. And while all of that was unfolding overhead, something happened on the ground in South America that a great many people have already decided is part of the same story. Part 10. 6 hours and 18 minutes. At about 1 in the afternoon local time on the 20th of August, the ground moved in the southern Peruvian Andes. The United States Geological Survey put it at magnitude 6.7. Peru's own Instituto Geofísico del Perú initially estimated 7.2, and that discrepancy is normal rather than suspicious. Initial magnitude estimates come from the first seismic waves to reach the nearest instruments, and refining them means waiting for the full waveform to arrive at stations around the world and then reconciling different measurement techniques. Early numbers move. They usually move downward. The epicenter was roughly 38 kilometers northwest of the town of Upahuacho in Parinacochas province in the Ayacucho region. The depth was 99 kilometers. Hold on to that number. 99 kilometers. We are coming back to it, and it is going to do more work than anything else in this part of the video. At least 2 people were injured. Homes were damaged along with health centres and schools, in a part of the country where a great deal of construction is adobe and unreinforced masonry, which is the building stock that performs worst under shaking. The tremor was felt across Ica, Arequipa, Huancavelica, Apurimac and Cusco, and it reached Lima. That combination, felt across half the country but with only 2 reported injuries, tells you something about the earthquake before we get anywhere near the sun. It is a signature of depth. A shallow magnitude 6.7 directly beneath a populated area is a catastrophe, because all of the energy is released within a few kilometers of the surface, and the shaking is violent and concentrated. Release the same energy 99 kilometers down, and the waves have to travel a long way through rock before they reach anybody, spreading out and losing amplitude as they go. The result is exactly what was reported, a very large felt area and comparatively modest damage within it. Peru knows the other kind. This is one of the most seismically active countries on Earth, because the Nazca Plate is grinding beneath the South American plate along its entire coastline, building the Andes in the process and storing enormous quantities of strain while it does. In 1970, a magnitude 7.9 off the coast of the Ancash region triggered a rock and ice avalanche off Mount Huascaran that buried the town of Yungay and killed tens of thousands of people in what remains one of the deadliest earthquakes in the history of the Western Hemisphere. In 2007, a magnitude 8.0 struck near Pisco and killed around 500. Against that history, the earthquake on the 20th of August was a serious event that Peru handled. It is not a mystery requiring an exotic explanation, and it is worth saying so plainly before we get to the exotic explanation people have reached for anyway. Now, the timing. The 8.1 solar flare peaked at 11:42 Universal Time. The earthquake occurred at approximately 1800 Universal Time the same day, 6 hours and 18 minutes apart. I want to be careful about how I handle what happens next, because there is a lazy version of this conversation, and I have no interest in it. The lazy version is to point at people who notice that pairing and treat them as gullible. They are not being gullible. They are doing the thing that human cognition is built to do, which is to notice that 2 unusual events happen close together and to ask whether they are related. That instinct is not a defect. It is most of the reason science exists at all. Somebody noticed that tides follow the moon, so let us take the claim seriously, and I mean actually seriously, which means building the strongest possible version of it rather than the weakest. Here is the strongest version. In 2020, a paper was published in Scientific Reports, Volume 10, Article number 11495, by Vito Marchitelli, Paolo Harabaglia, Claudia Tross, and Giuseppe De Natale. The title is On the Correlation Between Solar Activity and Large Earthquakes Worldwide. What they did was straightforward in concept. They took 20 years of measurements from the SOHO spacecraft, specifically proton density and proton velocity in the solar wind, and they compared that record against the global catalogue of earthquakes above magnitude 5.6 over the same period. They were looking for whether seismic activity showed any statistical relationship to what the Sun was doing. They reported that it did. Specifically, they found a correlation between proton density and the occurrence of large earthquakes, with a time shift of about 1 day, and they reported the statistical significance as a probability of being wrong lower than 10 to the -5. 2 features of that result are worth pulling out, because they are where the argument gets interesting rather than where it gets dismissed. The first is that the correlation was with proton density, not with proton velocity, and not with flares. That is a specific and slightly awkward finding. Proton density in the solar wind is not the quantity most people would reach for if they were trying to build a story about the sun shaking the Earth. Flares are dramatic and geomagnetic storms drive the currents we have spent this video discussing, and neither of those was the variable that showed the signal. Density is a measure of how much material is passing, and its connection to anything happening inside the Earth is considerably less obvious than the alternatives. The second is the one-day lag. A delay of roughly 24 hours is not what you would predict from a mechanism operating through induced currents, which would act essentially immediately once the disturbance arrived. A lag needs its own explanation, and the paper does not really supply one. None of that makes the result wrong. Unexplained correlations sometimes turn out to be real, and eventually get their mechanism, but it does mean that even at its strongest, the case rests on a statistical pattern connecting an unexpected variable to seismicity with an unexplained delay, which is a rather different thing from a demonstrated physical process. I want to be completely clear about what that means, because this is exactly the point where coverage of this subject usually goes wrong in one direction or the other. That paper exists. It was published in a Nature Portfolio journal. It went through peer review. Its authors are working geophysicists, and De Natal in particular has a substantial career in volcanology and seismology. Anyone who tells you this idea has never been taken seriously by any scientist anywhere is not telling you the truth, and anyone who tells you it is obvious nonsense has not read it. And the mechanism they propose is more modest and more interesting than the version that circulates online. Nobody is claiming the sun supplies the energy to break a fault. That claim would be absurd on its face, and none of the researchers working in this area make it. The proposal is about triggering, which is a fundamentally different idea, and the distinction is worth understanding because it applies well beyond this argument. A fault does not fail because something pushes it over. A fault fails when the stress accumulated across it, over decades or centuries of slow tectonic loading, finally exceeds the friction holding it in place. By the time a fault is close to that point, it is a system sitting at the edge of a threshold, and systems at the edge of a threshold can be pushed over by inputs vastly smaller than the energy they release. A boulder balanced at the top of a slope does not need much of a nudge, and triggering of that kind is real and established in seismology. It is not fringe. Tidal triggering is a documented effect. The gravitational pull of the moon and sun flexes the crust twice a day, producing tiny stress changes, and in certain settings there is a measurable statistical tendency for earthquakes to occur at particular points in the tidal cycle. Reservoir-induced seismicity is real, where filling a large dam changes the stress and pore pressure in the rock beneath and produces earthquakes that would not otherwise have occurred at that moment. Even seismic waves from a large earthquake on one side of the planet have been observed to trigger small events on the other side. So the framework is legitimate. Small perturbations can influence the timing of a rupture that was going to happen anyway. And the proposed solar version is that some electromagnetic coupling, perhaps involving currents induced in the crust, provides a similarly small nudge. It is also worth acknowledging that this is an old question rather than a modern internet invention. People have been proposing links between solar activity and earthquakes since at least the 19th century, when the 11-year sunspot cycle was first properly characterized and researchers immediately began testing it against every other periodic record they could find. Most of those attempts failed, quietly, and were forgotten, but the question kept being asked in every generation, because the intuition behind it never goes away. There is a very large energetic object nearby that visibly affects our atmosphere, and it seems reasonable to wonder whether it affects anything else. And there are related effects that are real, which muddies the water further. Earthquakes genuinely do disturb the ionosphere, for instance, but the causation runs the other way. The vertical motion of the ground and the ocean during a large earthquake launches acoustic and gravity waves upward through the atmosphere, and those waves reach ionospheric altitudes within minutes and produce measurable disturbances in the electron content overhead. That is a well-documented, well-explained phenomenon. It is also the exact opposite of what the viral claim asserts, and it is easy to encounter one and think you have found evidence for the other. That is the case. It is a real paper, in a real journal, proposing a mechanism from a family of mechanisms that genuinely exist, supported by a statistical result with a very small stated probability of arising by chance. It is a much better argument than most people assume. It is also, when you apply it to what actually happened in Peru on the 20th of August, not nearly good enough. Part 11. 99 kilometers down. 99 kilometers. That is the number I asked you to hold, and it is the first of 3 separate reasons this particular claim does not survive contact with this particular earthquake. Any one of them would be enough on its own. The Peru earthquake was not a shallow crustal rupture. At 99 kilometers deep it occurred inside the Nazca Plate, the slab of oceanic crust that is descending beneath South America and building the Andes as it goes. That is an intermediate depth event, and it is a different animal from the shallow earthquakes most people picture. It happens inside a slab of rock that has already been driven down into the mantle, under pressures where ordinary brittle fracture should not be possible at all, which is why the physics of intermediate depth earthquakes involves processes like dehydration of minerals within the descending slab rather than simple frictional slip. Now put that next to the proposed mechanism. Geomagnetically induced currents flow in the ground. Ionospheric current systems flow 100 kilometers up in the atmosphere. Both are surface and near-surface phenomena, and the currents induced in the Earth are concentrated in the upper crust, in the most conductive layers, in the top few kilometers. The energy involved does not reach 99 kilometers down into the mantle in any quantity that means anything. This is not a case of a weak effect. It is a case of no plausible pathway at all. Whatever the sun did on the 20th of August, it did not do it in the interior of a subducting slab 100 kilometers beneath the Andes. That is closure number 1. Here is closure number 2. Even taking the trigger framing at its most generous, look at what it actually claims. It says the fault was already at the point of failure, loaded by tectonic processes over centuries, sitting at the edge of rupture. And it says a small external perturbation determined the moment it let go. Follow that through. If a fault is genuinely that close to failing, it is going to fail. Not eventually in some vague sense, but on a timescale that is trivially short compared to the centuries of loading that got it there. Days, weeks, months, perhaps a few years. Which means the very best version of the solar trigger claim is not that the sun caused an earthquake. It is that the sun influenced the timing of an earthquake that was already imminent by an amount that is invisible against the geological clock. That is a considerably smaller claim than the one circulating, and it is worth noticing how much it shrinks under examination. It goes from the sun broke the earth to the sun may have adjusted the schedule of something already in motion, and it makes that journey without any of the underlying physics changing at all. And then closure number 3, which is the one I would ask you to remember longest because you can use it on almost anything. Earth produces roughly 130 to 150 earthquakes of magnitude 6.0 or greater every single year. Do the arithmetic out loud. That is 1 every 2 to 3 days, somewhere on the planet, continuously, in a normal year, with no solar involvement of any kind. Meanwhile, active region 4513 produced 6 M-class flares in 40 hours. When you have 2 phenomena, each occurring on a timescale of days, and you go looking for a pairing between them inside a 24-hour window, you will find one. Not sometimes, essentially always. The coincidence is not evidence of a connection. It is a straightforward consequence of the frequencies involved, and it would keep happening at exactly the same rate, in a universe where the sun and the Earth's interior had no relationship whatsoever. There is a further trap hidden inside that, and it is the one that catches careful people rather than careless ones. Notice how many choices are available when you go looking. You can choose the window, 6 hours, 12, 24, 48. You can choose which solar quantity counts, flare class, proton density, solar wind speed, KP index, sunspot number. You can choose the magnitude threshold for the earthquakes. You can choose whether the earthquake comes before or after. Each of those choices is individually reasonable. Multiply them together and you have hundreds of ways to slice the same 2 datasets, and if you test enough of them, some combination will produce an impressive-looking result purely by chance. That is not fraud, and it does not require anyone to be acting in bad faith. It is a well-known statistical hazard, and the defense against it is to specify what you are testing before you look, and to correct for how many comparisons you made. That is why finding one pairing tells you nothing. To learn anything, you have to do what the researchers actually did, which is take 20 years of data and ask whether the rate of pairings is higher than chance would produce. And when other people did that, they got a different answer. In 2013, Jeffrey Love of the United States Geological Survey, and Jeremy Thomas of Northwest Research Associates published a paper in Geophysical Research Letters with a title that does not leave much room for interpretation: Insignificant Solar Terrestrial Triggering of Earthquakes. They tested sunspot number, solar wind velocity, and geomagnetic activity against the global earthquake record. Their method was to split the record according to whether each solar terrestrial measure was above or below its median value, and then compare the earthquake number distributions between the two halves. If solar activity influenced seismicity, the busy half should look different from the quiet half. It did not. They found no consistent, statistically significant difference. There is a detail in how that study came about that I find genuinely revealing. Love has said the work was motivated by interest from the popular press, following a couple of large and devastating earthquakes, which is to say, this study exists because the public kept asking. Scientists at a government agency heard the question circulating, thought it was worth answering properly rather than dismissing, went and did the analysis, and published the result. That is not what a cover-up looks like. The USGS position today remains that there is no evidence that solar flares or magnetic storms cause earthquakes. So where does that leave the 2020 paper? Contested, and openly so. A formal matters arising comment was published in response to it, which is the mechanism a journal provides for a substantive technical challenge to a published result. Seismologist John Vidal of the University of Southern California expressed deep skepticism about the conclusions, and the authors themselves, when defending their work, conceded that the physical mechanism might not be appropriate, while maintaining that the statistical correlation was hard to deny. I want to give that concession its due because it is honest and it is unusual. What they are saying is, we found a pattern in the numbers and we cannot explain it. That is a legitimate scientific position. It is also, on its own, a very long way from a demonstrated causal link, and it is nowhere near enough to attribute one specific earthquake at 99 kilometers depth to one specific flare 6 hours earlier. While we are here, there are two other claims that will come back if anything happens in the strike window, so let us deal with them now. The first is the Internet apocalypse. That phrase traces to a conference paper from 2021, examining the vulnerability of undersea communication cables, and the underlying concern is real, but much narrower than the headline. Optical fibre carries light. Light does not care about magnetic fields, and the fibre itself is unaffected. What is vulnerable is the electrical conductor running alongside the fibre to power the signal repeaters spaced along the cable, and induced currents in that conductor are a genuine engineering concern, particularly on long high-latitude routes. The realistic failure mode is regional cable outages that take time to repair. It is not the Internet ceasing to exist. The second is that agencies know more than they are saying. Every single number in this video came from public feeds. The flare times and classes came from the published GOES X-ray sensor record. The region positions came from the Solar Region Summary, which the Air Force and NOAA publish daily. The forecast probabilities came from the 3-day forecast, published continuously. Anyone watching this can download all of it right now and check my arithmetic. Back on the 17th of August, we ran into precisely the same pattern with magnetic pole drift, where the supposedly suppressed information turned out to be sitting in a published model that anyone could read. The data is not hidden, it is just not read. And now the point that all of this has actually been for. This was a rehearsal. If active region 4513 produces an X-class flare during the strike window between the 23rd and the 27th, and a significant earthquake occurs somewhere on Earth within a day of it, that will not be a remarkable coincidence. Given a rate of 1 magnitude 6 or greater every 2 to 3 days, it is close to the expected outcome. And the claim you have just watched me build and dismantle will come back immediately, at 10 times the volume, attached to a much bigger flare and a much louder news cycle. You will already know how to think about it before it arrives. Ask about depth, ask about energy, ask about base rates, and ask whether anyone has checked 20 years of data, or whether they have simply found one pair of events and pointed at them. Part 12. What 2.6 trillion buys. There is a number attached to the worst version of this, and it is worth ending on because of what its size actually tells you. The National Research Council's 2008 assessment of severe space weather and Lloyd's of London's 2013 study of solar storm risk to the North American electric grid converge on an estimated economic cost for a Carrington-class event for the United States alone of between $600 billion and $2.6 trillion, 20 to 40 million people affected, restoration times ranging from 16 days to 1 or 2 years. Look at that range for a moment rather than past it. 600 billion to 2.6 trillion is a factor of more than 4. That is not a rounding error or a modelling nicety. A spread that wide is an admission that the people producing the estimate do not know which side of a critical threshold the event would land on. And they have been quite specific about what that threshold is. It is whether extra high voltage transformers are merely tripped offline or physically destroyed. Everything hangs on that distinction. A tripped transformer is a transformer that is fine. Protective systems noticed something wrong and removed it from service, and once the storm passes you inspect it and put it back. Hours, at worst days, and the cost is the value of the electricity you did not deliver. A destroyed transformer is a different category of problem entirely. As I described earlier, these are custom-built machines weighing hundreds of tons, engineered for one position in one network, with manufacturing lead times measured in months, and a small number of facilities worldwide capable of building the largest of them. Spares exist, but they are held in ones and twos, because holding a large inventory of bespoke 100-ton objects against an event that might not happen this century is not a decision any utility board has ever been able to justify. The scenario nobody has provisioned for is not one transformer failing. It is many of them failing at once, across a continent, in a single afternoon, against a supply chain built for occasional individual replacement. And restoration in that scenario is not linear, which is the detail that makes the long end of the estimate credible rather than hysterical. You cannot bring a grid back piece by piece without the equipment that manages the bringing back. Restarting a large power system requires generating stations that can start without external power, and then a carefully sequenced process of energizing transmission paths and picking up load in increments. And that process runs through exactly the high-voltage equipment that the scenario has removed. Damage enough of the machinery of restoration and the restoration itself becomes the bottleneck. That is what the gap between 600 billion and 2.6 trillion is measuring. Not uncertainty about the sun, uncertainty about our own equipment. I do not want to leave you with the impression that this is a hazard nobody is doing anything about, because that would be inaccurate and it would also be the least useful thing I could tell you. A great deal has changed since 1989. Grid operators in most developed countries now have written procedures for what to do on receipt of a geomagnetic disturbance warning, and those procedures are specific. Reduce loading on the transmission paths known to be most exposed, bring additional generation online so that the system is not operating close to its stability limits, cancel scheduled maintenance that would remove redundant capacity, and in the most severe cases deliberately shed load to protect the equipment. Geomagnetically induced current monitors are installed at vulnerable substations. Vulnerability assessments are, in a number of jurisdictions, a regulatory requirement rather than a voluntary exercise. Satellite operators have their own playbook: safe modes, suspended maneuvers, delayed launches, and postponed spacewalks. Airlines have polar route contingency plans. There are engineering solutions for transformers as well, including neutral blocking devices that stop quasi-direct current from entering the winding in the first place, and they work. They are simply expensive, and they have been deployed selectively rather than universally. The honest position is that the difference between a well-prepared grid and an unprepared one during a severe storm is enormous, and a substantial part of the world's infrastructure now sits somewhere in the middle of that range. The warning time is real, the procedures are real, and they meaningfully reduce the damage. What they do not do is eliminate it, and none of them have ever been tested against the top of the scale. Two smaller things to close out, both of which put this in proportion. The first is that none of what the Sun has done this week is abnormal. Cycle 25 peaked in October of 2024, and we are on the declining side, and a region producing 6 M-class flares in 40 hours during the declining phase is entirely consistent with how these cycles behave. The Sun is not doing something new. It is doing something ordinary, and ordinary for a star includes a very long tail. The second is a piece of timing that almost nobody noticed. As active region 4513 rotates onto the disk, active region 4507 is rotating off it. 4507 was the genuinely complex one, the beta-gamma delta region, 300 millionths of the hemisphere, 13 sunspots, the only configuration on the visible sun that textbooks associate with the largest flares. It is leaving, and the region replacing it is the one nobody can classify. The dangerous-looking one is departing, the unreadable one is arriving, and the difference between those two descriptions is entirely a matter of what angle we happen to be looking from. Step back far enough, and that is the whole situation, and it extends a great deal further than one sunspot. There is a star 93 million miles away that has been doing this for 4.5 billion years. It threw off flares and clouds and particle storms through every previous era of life on this planet, and none of it mattered, because there was nothing here that cared. It kept doing it through the entire history of our species, right up until about 170 years ago, when we started stringing copper wire across continents. The sun did not change. We changed, and in changing we built something that could be reached. And we know it did more than we have ever seen, because the evidence is written into wood. In 2012, a Japanese researcher named Fusa Miyake was measuring carbon-14 in the annual growth rings of ancient cedar trees, and she found something that should not have been there, a sharp spike in the year 774, far too large and far too sudden to be explained by anything in the normal record. Carbon-14 is produced in the atmosphere when energetic particles from space strike nitrogen atoms, so a spike in one year means a flood of particles in that year. The signal has since been confirmed in tree rings on multiple continents and in ice cores, and a second event of similar character was identified in the year 993. The most widely accepted explanation is an extreme solar particle event, and the estimates put it at something like an order of magnitude beyond anything in the instrumental record. Not larger than Carrington by a little, larger by a lot. Nobody wrote it down because in the 8th century there was nothing to notice. There were no wires, no satellites, no navigation signals, no grid. The most extreme thing the sun is known to have done to this planet passed without a single human being recording that anything had happened at all. We only know about it because a tree kept a record that nobody was reading for 1200 years. And every piece of the technological world we now live in, the grid, the satellites, the navigation systems, the timing signals that financial markets and communications networks depend on, all of it was designed and built and scaled during a window of about 70 years in which the sun happened not to deliver anything at the top of its range. We have never run this civilization through a Carrington event. We have only ever run it through the small ones, and the small ones have already cost us 38 satellites, $565 million of corn, and a dark province in March. We have always assumed the sky above us is the one place nothing can come from. But what if the only reason it has stayed that way is that we have not yet been standing in the wrong place at the wrong moment? So here is where we actually are tonight. 6 M-class flares in 39.5 hours. A classification in an official column that reads beta, which almost nobody in the field believes is a true description of the region it describes. A rotation carrying that region 13.2 degrees closer to us every day, into a strike window that opens on the 23rd, a magnetosphere that has been sitting in a high-speed stream, a satellite fleet accumulating charge, and a region that has not stopped firing, that fired twice again this morning, that reloaded in 9 minutes. Somewhere around the 22nd or 23rd of August, active region 4513 will rotate far enough from the limb for the instruments to get an honest look at it, and a magnetogram will come back with a real classification on it. It will say one of 3 words: beta, beta gamma, or beta gamma delta. Nobody knows which, and whichever one it turns out to be, we will be finding out at almost exactly the moment that region arrives in the one position where the answer stops being academic.